Hi everyone. In this the second video, I want to continue on the derivation of that ideal gas equation from kinetic molecular theory. So remember that what we ended in the first video is this equation. We say that we can basically start from what we often call scientists often call first principles, things that are very simple, from very simple assumptions to get to an equation that looks very much like what we observe experimentally. Okay, so here from theory we get PV equals N times 1/3 times m, which is the mass of a particle, times u squared, this is something called the average velocity, or as you'll see in a second, called root mean square velocity, times Avogadro's number. And that expression looks very much like PV equals nRT, which is of course their experimentally derived equation. Okay, now so what we want to do now is, using these two equations, relate them to each other, so then we have some explanation as far as what is the meaning of some of these macroscopic properties. So the first one we want to talk about is this term called the RMS velocity, or here it's written in its full term, which is root mean square velocity. This is nothing more than the average speed of a gas particle in a collection of gas, like in 1 mole of gas, for example. So if you think about it, in 1 mole of gas you have 6.02 times 10 to the 23rd particles of gas. On the average speed of each of those gases is going to be given by this RMS velocity. Now, how do we derive an expression for this RMS velocity? Well, basically, if you look at the previous equation, you see that the whole thing here that's in the parentheses, 1/3 mu squared times Na, is equal to RT, right? Because everything else can be canceled. If I take a ratio of these two, I can see that, or if I say PV over N is equal to this, then PV over N is equal to RT here. So in other words, this whole thing is equal to RT, okay? Which is what I wrote here. And so the RMS velocity itself is this U term that we're trying to get to. So first we isolate the U squared. Now the U squared with a bar on it on the top, with a line on it on the top, that's just the average after squaring the velocity. So if you remember, when we talk about standard deviation, we do something very similar. We take a difference, and then afterwards we square we square the differences, all the difference from each measurement with the average, each one of them, and then we take an average after that, right, of that the sum of all of those squares. So that's what this number is representing, and this is a common kind of statistical method to take averages if you have a huge number of particles. So in this case, we say that the U squared, because of all of these things, right, this is equal to that. If I isolate U squared, what I get is RT over M times Na, and then the 3 goes to the top, so 3RT over M times Na. Now, the 3RT remains the same, but if you think about it, M is the mass of one particle, Na is the number of Avogadro's number of particle, which is 6.02 particle per mole of particle. So then you have a mass, which is something in units of grams per one particle, times something that has a unit of particle per mole. So your unit, after you multiply these two, becomes grams per mole, which of course is the unit of molar mass. So this M here is your molar mass, okay? And so this is equal to U squared. This 3RT over M is equal to U squared, which is the velocity squared. We just want the velocity, we don't want the velocity squared. So just the velocity alone, which is, this is what we call the root mean square velocity, is equal to the square root of 3RT over M. Again, R in this case is the universal gas constant, T is temperature, and M is molar mass. Okay, I want to emphasize before we move on that the value of R that we're going to use for these type of calculations involving speed and kinetic energy, which is on the next slide, is this value right here, 8.314 joules per mole Kelvin. Okay, so we're not going to use the one that we've been using up to this point, which is R is equal to 0.0821 liter atmosphere per mole Kelvin, because That value of R is useful when we're talking about calculations involving pressure and volume. In this particular case, we're talking about calculations involving energies. And so when we want to calculate energies, we have to use units that are units of energy, which is what a joule is. So 1 joule is actually equal to 1 kilogram meter squared per second squared. Now you might not, it might not be immediately clear to you why this is a unit of energy, but energy is one definition of energy is the amount of force applied to move an object a certain distance. Remember, I mentioned that in a prior video. So the unit of force is kilogram meter per second square, and if you multiply that by distance, which changes how far this object has been moved, then it becomes kilogram meter square per second square, and that's what the joule comes from. So you can actually convert from the one unit of R to the other one, from the 0.0821 liter atmosphere to 8.314 joule. You just need to know what the actual SI units are for a liter and for atmosphere and so on, and you can convert them. But we're not going to do that here. It's not that important. But just remember that when you're doing these type of energy related calculations, you're going to use R in this value. Okay? Now, as I mentioned in the first video, I said that we were deriving this equation, and I said if you don't want to worry about the derivation, you don't understand it, you don't care for it, that's fine. But this is one of the two equations you need to remember, this RMS velocity equation, because this is a really important equation. It allows us to calculate basically on average how fast is a gas particle moving at a particular temperature. Okay, so you can see that this is a function of temperature, so as temperature goes up, velocity goes up. Okay, average velocity goes up. But also you see that it's inversely proportional to molar mass. So in other words, what that tells you is that if a particle has a higher molar mass, in other words, a heavier particle, it has a lower velocity. And something that has a lower molar mass, a lighter particle, would have a higher velocity. So that should make sense, right? Something that's bigger would be slower, something that's smaller would be faster. The second equation you need to know is this equation for total kinetic energy. So we haven't gotten to the topic of energy yet, which we will get to in the next chapter when we talk about thermochemistry. But at this point, you just have to kind of take it, again, this comes from physics, that the kinetic energy of a particle, if you're just kind of considering one type of motion, like translational motion, for example, it's going to be half times mu squared, okay, where m is the mass of the particle and u is the velocity of the object. So in other words, if a car is moving at 60 miles per hour, 60 miles per hour is its velocity, and if you square that velocity and you multiply that by the mass of the car times a half, you get the value of the kinetic energy of that car. If I'm running, then if you take my mass multiplied by the square of my speed times half, then that you get my kinetic energy. Okay, so again, kinetic energy is the energy of motion. You can do this for particles as well, right? If you have one particle that's moving at a certain speed and has a certain mass, you can calculate its kinetic energy. Now remember, if we're talking about 1 mole of particle, then we don't write it just this, but we would say it'd be half times m times 1 mole, which is of course Avogadro's number, times u squared. But because we now have a bunch of particles, we do an average velocity, and that average velocity is of course the RMS velocity squared. Okay, so then kinetic energy for 1 mole of particle would be just half, really just half mu squared times Na, but the Na here is Avogadro's number, the u squared is the RMS velocity squared. Now we just derive an expression for the RMS velocity in the previous slide, which is this, and before we take the square root, it just u squared just looks like that, right? 3RT over m, or 3RT over m times Na, okay, the small m. So what I would do is take this expression 3RT over m times Avogadro's number and plug that back into, substitute the URMS expression with that. Okay, so then I'll have half times mass times Na times 3RT over m times Na. This just comes straight from the previous slide. Okay, So what you can see is this expression cancel, right? The m times na cancel. So what I'm left with is just kinetic energy is equal to 3/2 RT. Now this is what we call the total kinetic energy of 1 mole of any gas at a particular Kelvin temperature. So if your temperature is at 273 Kelvin, you're going to have a certain kinetic energy, total kinetic energy associated with that 1 mole of gas. So this is per mole of gas. This is actually has a very important meaning, which we'll discuss in the next slide, and we'll do an example in the next video, and we'll do an example as well there. But again, I want to emphasize here that the R that you would use for this type of calculations would be the R that has the energy unit, which is 8.314 joules per mole Kelvin. Okay, so again, this is the expression of the kinetic energy. Now remember, I said that there's two equations that are important. The first one was our RMS velocity equation. The second one was this kinetic energy equation. So if you don't want to remember derivation, these two you have to remember. Okay.